But when I record it on my computer like I'm doing right now, I can throw it onto YouTube and it'll live there as long as YouTube is alive, which is who knows how long. Okay, so if nobody has any questions, then we are going to move forward. Just a reminder, when is your next test? Well, let's see. Zoom folks, I'm not sure if you can see what's about to pop up, so I'll share it real quick. Let's see. Looks like the 1st, which is a week from Monday. That does not allow a day for review, but what I will do is I will, first off, I will provide you at a bare minimum the list of things that you need to be able to do and maybe point you towards some specific homework questions. What I will try to accomplish between this Wednesday, the 25th, and this Monday, the 1st, is, oh, wait a second. Monday's not the 1st, is it? Yeah, it is. Right? Okay, that means the Wednesday is the 3rd. Your test is going to be on Wednesday. It will not include 5.1. But what that will give us an opportunity to do is once we finish 4.4, I don't like giving a test the day after I cover something. It gives you no time to get feedback. By moving the test to this Wednesday, instead of having it on this Monday, I give you the assignment on Wednesday, you do your homework, you take a quiz, whatever. And then when I see you again on Monday, you can ask me questions about that homework so that I can test you the next time. Does that make sense? Okay, I just don't think it's fair to say I'm going to teach you something now and give you a test the next time I see you. There's got to be some in-between time to get feedback and questions answered. So now that doesn't mean we're not going to do anything on that Monday. We do need to move on to chapter 5, section 1 that Monday. So on that Monday, we'll just answer homework questions and move on to the next section like we normally would, with the understanding that you'll have a test over chapters 3 and 4 on this Wednesday. Okay, so I'm glad I caught that now. Unfortunately, I don't have as much flexibility down here because this is the last regular class day. Now, I can tell you something about final exam week. Ever since I've taught here, the Monday of final exams has been a dead day. No classes, no finals. The exception was classes that met only on Mondays, which is not us. So what that means is on this Monday, it will not be our final exam, but I'll be available. You'll probably be available. So this day will probably be an optional review session. I'm going to put optional because I can't require you to be here on that day. And I'm going to make this fit into this cell. Give me 1 second. We'll take it down a couple of notches and then we'll tell it to wrap the text. Okay, so I forgot that the first Monday of final exam week is always a dead day. I'll double check with the final exam schedule, but I'm pretty sure that's still going to be the same, which means that we won't have class this Monday, but I will be up here during class time to conduct an optional review session, a Q&A session. I will give you materials to prepare for the final, a review, if you will, and this will be the day that you come to ask questions or I give you any more information about the final exam. I will record that on Zoom and make it available to watch later. You are probably correct that it is in the wrong place. When I create an assignment, when I create any assessment in Canvas, I have to choose where it goes. And sometimes I forget to tell it, count this as a quiz. Because if it lands up here, then nothing up here counts towards your grade. Yeah, it keeps track of attendance when I take it. And I'll admit, I don't take it as often as I should. And if you look in your grade book, it has a grade for your attendance, but I promise you, it is not counted as part of your grade for the class. But when I drop something accidentally like quiz 5, it is also not counting towards your grade, which it should. So thank you very much for catching that. It is in there now. I appreciate that. I always appreciate a second set of eyes. All right. But as I was saying, when the final exam, excuse me, what's going on here? Share this. Maybe it's been sharing it. I don't think Zoom folks saw what I just did. Don't worry, Zoom folks, if you missed me moving the quiz into the quiz category, no big deal. But getting back to the final exam week, do y'all know where to find the final exam schedule on the TJC, on the UT Tyler website? Can somebody find that real quick? Well, oh yeah, I guess I could do that. I'm on a computer, aren't I? You know, sometimes you can't see the forest for the trees. Let's do that real quick. We'll pretend I am you going to the UT Tyler website and searching final exam schedule. And spring says spring, but I bet it's fall. Yeah. All right, let's see if I'm correct. The Monday of that week is December 6th, I believe. And it looks like there are some final exams scheduled for that Monday. That would be the late Monday, Wednesday classes. This is not us. We meet at 5:30. So our exam, wait a minute, y'all aren't stats 2. Scratch that. We meet at 4 o'clock-ish. So here's our final exam time slot. So our final exam is Wednesday, December the 8th, but it doesn't start until 5 p.m. But wait a minute, my next class, seriously? Because I have a class after you and that's not when they meet. They meet at 5:30. And their exam is after y'all. So I'm going to be here late that day until 9:15 p.m. Oh, well, but this does confirm what I said earlier. We don't have class on that Monday. It's a dead day. There are some exams on Monday, but only for classes that meet at 7 p.m. or 8 p.m. or meet only on Mondays, but everything else is on Wednesday or Friday if it's a Monday, Wednesday class. So unless some of you have a class, does anybody have a class after mine today? What time is your class after mine? So right after this class? Okay, so you're going to be in for a heck of a Wednesday because according to this, you're going to have both of your exams, mine and the one after this, on the same day back to back. Just a writing class. Oh, well, cool. Good for you then. Good for you. But I don't think any of us have. Do any of you have a class that meets after mine, but only on Mondays? No? Okay. So what this means is none of you have a final exam commitment on the Monday of final exam week. So what we will do on Monday, December 6th at regular class time, there shouldn't be anybody in here because we're in here at this time, not these people. So this room should be available the Monday of final exams. So during regular class time, 4:05 to 5:30, no, 40. What time do we end? 5:30. We end at 5:30, right? Okay. This is what was this, week 9? And I'm asking you, when does the class end? I will have an optional final exam review session in here the Monday of final exam week at regular class time. It will be optional. You are not required to attend. I will be running a Zoom session simultaneously. I will record it. I will make it available to you. But if you can attend the Zoom session or be in the classroom, then we can have a Q&A session in preparation for your final exam, but it is optional, which of course means it's not required. And your final exam will be on Wednesday, December 8th. And since we start at 4:05, that's pretty much that time slot. It will be from 5 p.m. until 7 p.m. Now, can you have more time on your final? I don't know how early this room will be available prior to us. The class that meets before us has their exam until 4:45, so probably not. But my other class has their exam on the same day in this room immediately after y'all, which means if you need more time on the final, you can just stay in here as I start that next final exam. Okay, so it's 2 hours, but and for those on Zoom, I'm doing 2 hours in air quotes, but I can allow you extra time. How much extra time? Not gonna lie, I plan on being here until 9:15. Should any of you take 4 hours and 15 minutes to do this final? No, you shouldn't, but you would have that option. Okay, so that's a little bit comforting because I was worried about not having a time to review for the final exam, but we will have a review session, but it will be optional attendance. I guess technically every day is optional. I'm not going to penalize you for not being here. You have a teacher that says if you miss 3 or more classes, I'll lower your final letter grade by 1 letter. I think that's silly, personally, because my opinion is this: if you can do the material outside of class, more power to you. But if you can't and your grade's going to lower itself, I don't have to help it. It'll do it on its own. But anyway, that's just my opinion on that. And I know there are people that I work with in this department that have policies like that, but that is their prerogative. It's just not something I necessarily agree with. Okay, well, I guess we can go ahead and get started with the material, since nobody had any questions from 4.1. Yes, Max. Do we have an SI? Good question. I've never been approached this semester with a student asking to be an SI for this class. So right now, I think the answer is no. Now, there actually is a student who is in this class who is often not in this room, who was an SI for me before in a different class. And that student might be an SI for something else. But as far as an SI assigned to this student, to this section, I was never approached with an SI person. So I know SIs exist for statistics, but for whatever reason, there's not one for this particular section. Now, for a course that's offered with multiple sections like statistics, if there's an SI for a different section, is that something that y'all can capitalize on, or does it have to be dedicated to this section? Go through from different sections. Okay, so do SIs exist for statistics? I'm pretty sure they do. I just don't have one specifically assigned for this section. All right. Good question. Probably would have been a better question about 7 weeks ago, though. Yeah, let's talk about when that's going to happen and when it's going to be due. The short answer to when it's going to be due is close to the end of the semester. The project that I'm going to assign you actually involves probably 6.1. Yeah, it's going to involve 6.1. Where you have to go get a proportion statistic from the Gallup website. Gallup says, what was the one I showed you last time? 37% of people say football is their favorite sport. So you're going to go to that website. You're going to find some proportion that they claim. You might have to search some topic that you like. And then you're going to test that doing a hypothesis test. We haven't gotten to the details of how to do that yet, but we will. And you're going to do that by surveying 50 people and asking them the same question that the website asked. Now, the website might ask something like, what is your favorite sport? And then you have to filter through all the answers. But for the purposes of testing a specific claim, like 37% of people prefer football as their favorite sport, you could just ask people, is football your favorite sport? Yes or no. You really want to ask them a binary question that has one of 2 answer choices. So probably a yes, no question is what you'll ask these people. And then once you ask these 50 people, what you're going to do is you're going to get a p-hat for that sample. What proportion of my sample had the same answer as the survey? And then it probably will not be the same as the percent on the website. And then you're going to go through the steps of doing a hypothesis test. The actual work is very short. The hardest part about the project is finding the proportion you want to test. So you got to troll through the website some and find a number. I would search a topic of interest, something political, something socioeconomic, something involving, I don't know, just whatever interests you. And search something and say, I wonder what percent of people say something. Search a keyword, find a proportion that they suggest from their website. And then the second hardest part, well, I don't know which is harder, coming up with the question you're going to ask and the statistic on the website you're going to test, or surveying 50 people and getting their answers. The instructions on the project will say you can get the answers however you want. You can do a Facebook survey. You can go on Facebook or whatever social media you want. Hey, I'm doing a stats project. I need you to answer this question. But if you do something like that, make sure you tell them No commentary, no opinion. I just need a yes, no answer, because you know how people on Facebook are, or any other social media. So just yes or no. And isn't there a way to put a poll or something on? Okay, so you could do that too. You could do that too. And you can get more than 50 people, but I want it to be at least 50 people, because I want to have it a little bit of statistical significance. So you'll get your p hat from your sample. You'll get the value of p, the proportion, population proportion, from the Gallup website, and then you'll go through the steps of doing the hypothesis test. Doing the hypothesis test will be quick and easy. It will take you like maybe 5 minutes to do it. It's just getting to the point where you're ready to do it that takes the work. And then you will send me your data, and then you'll write up the results and you'll give me that as well. So the actual project itself doesn't take much time once you've decided what it's going to be about and once you gather your data. Yes, sir. No. In fact, I will explicitly say, do not gather any identifying information from the people you talk to. No names, no genders, unless the question's about gender. Nothing that can say, oh, I can trace this answer back to that person. Because if you do, then we have to go through HR and other places on campus to get consent forms to participate in the survey. But as long as you gather data that cannot be directly related back to the person that gave the answer, then we're in the clear and we don't have to cover our backs. So absolutely not. And it will be in the directions. Don't write anything down except their answer and nothing else. Okay, cool. Good question. And thank you for asking me about that. But again, the math that we have to learn before you can do this project is in chapter 6, section 1. But trust me, it's a real quick thing to do once you have the data. That's really the hardest part about statistics, is gathering the data in the first place. Ideally, you want a representative and random sample, which isn't always that easy to get. I'm just going to ask you to talk to 50 people, whether it's on social media, you stand out in the parking lot, and you may not even have to ask somebody a question. You might just be wondering, gee, I wonder how many cars who park on campus also have a TJC parking sticker. So you just walk through a parking lot. Yes, no, yes, no. So, but then again, you're not going to find a percent on the Gallup poll that says such and such percent of the population has a TJC parking sticker. But there may be some questions where you can gather the answer observationally without talking to people. Okay, so keep that in mind when you're going through this, when you do this project, that you're going to be gathering data and you may have to ask people to answer a question. But, if you want to make it a little bit controversial, go fine. Think of a controversial topic. Get on Gallup and search that and see what percent you can come up with that you're going to test. And then at the end, I will ask you if you reject the website's claim. Gallup says 40% of people like this. My results were I rejected that. Speculate why you think your sample came to that result. For example, if and I'm just making up numbers here, I have no clue how accurate these numbers are. If you looked it up and it said 73% of people support a woman's right to choose to have an abortion, and then you survey 50 people and you come up with like 25%. And then your evidence is strong enough to reject the claim on the website, then you speculate why you think that happened. Well, we live in a conservative state in general, so there's probably more people that would say no than yes, or something like that. And again, I'm totally making up numbers, and I'm not trying to put any preference on one side of the issue versus the other. I'm just saying that if you come up with a reason to reject the claim, if your hypothesis test ends up rejecting the website's claim, which will be your null hypothesis, then just try to speculate. And that's all I'm going to ask you to do, is speculate. I'm not going to check to see if your reason is right. Why do you think your sample disagreed strong enough with the website's claim to end up rejecting their claim? That's all. It's just a speculation. The only way you miss that part of the project is if you don't answer it. Now, if you don't reject their claim, then there's nothing to speculate. Yep, my sample agrees with you. Or rather, my sample wasn't strong enough to reject you. But if it was strong enough, then you say, well, maybe the reason my sample was strong enough to reject this is because the way I picked my sample or where the sample came from, or no, their claim really isn't right. I think it's wrong for the following reasons, but it's a speculative answer. All right, we need to go ahead and get started with the next section, 4.2. But in order to do that, I want to quickly remind you what happened in the previous section. If you have any further questions, I recommend hanging around at the end of class to get them answered. So let's quickly recap, hopefully quickly recap the main things from section 4.1. The first thing we talked about were hypotheses. And remember that a hypothesis is a claim about a population parameter. I probably did not use those exact same words last time, but it should convey the same idea. It's a claim about a population parameter, and more specifically, a claim that allows equality. Just as a reminder, does anybody remember the notation for null hypothesis? It's capital H subscripted with an O or a 0. For example, we could say that the proportion of people who eat at McDonald's is 35%, just making up a number. Or we could say something like what else could we test? We could test two populations at the same time. We could say that the average number of the average salary for men is equal to the average salary for women. So we could test two populations simultaneously, but that would be the null hypothesis. Just as a reminder, and I'm going to type it over here. Oh, back. Sorry. I need to take something back. When I said a hypothesis is a claim about a population parameter, a claim that allows equality, I was blending two things together. That is what a hypothesis is. But there are two types of hypothesis. The null hypothesis is a claim that allows equality. That's my definition of it. The author's definition is it's the status quo, or it's the hypothesis that says that nothing is different than what we would expect. I really don't like those definitions because they're a little froofy. Technically speaking, the null is a claim that allows equality. And when I say allows equality, that means that it can be equal, but it could also be greater than or equal to, or it could be less than or equal to. All three of those relations allow something to be equal. This author's perspective is it's always going to be equal, but they kind of make a side note that says, well, it could be these other two also, but we're always going to make it equal. And I will probably always use equal as well. Every once in a while, though, we should really use one of the others. For example, if I said at least 35% of people go to McDonald's, well, let's flip that. Who in here is at least 21 years old? Is anybody exactly 21? Okay, so your hand should be up. If you're at least, so when I say at least 21, that includes being equal to 21, right? So this, I know it says greater than or equal to, but you could use that to say at least a certain value, or the opposite of it, at most. Is anybody here at most 18? Okay, so y'all are 18, I assume. Anybody under 18? No? Okay, but you're at most 18. So when I say at most 18, that means you're less than or equal to 18. So those are classic examples of hypotheses that don't explicitly demand equality, but they allow it. I'm at least 21. I can vote. I'm at most 18. I'm not sure what happens once you surpass 18 that you can't do prior to being 18, but you know, those phrases often invoke some version that allows equality. But for our purposes, the null hypothesis will almost always just say something equals something. And by contrast, the alternative hypothesis, what was the notation for alternative hypothesis? Not HO, HA, or H1. Now I will be using HA as a default. If I accidentally write H1, my apologies, but I do want to be consistent with the way the alternative hypothesis is represented in the textbook. The alternative hypothesis, by contrast, the alternative never allows equality. I'm going to shrink that down so it fits on one line. That will work. And I guess if I'm going to do that there, never mind. The alternative never allows equality. Now, unlike the null hypothesis, the alternative hypothesis can contain one of three relations. The one that explicitly says not equal to looks like that, but it could be less than, and it could be greater than. And we will encounter all three variations because each variation invokes a different they all invoke the same process, but each of those three relations invokes a different step at one of the particular moves in the process. Now, without further context, it's impossible to say what the alternative hypotheses would be for these two stated null hypotheses. So let's put these in some context. I say that 35% of all Americans go to McDonald's, as I hold a drink from McDonald's. And somebody says, yeah, you ever seen the drive-through? Pretty sure it's more than that. If I said, yeah, I think it's more than 35%, does anybody know what the first alternative hypothesis would be? Yeah, if I said, well, I think it's more than that. You say P equals 35%. I say it's greater than. And again, it's contextual, because if I said 35% of people fail my class, and the registrar gets wind of this and they say, we need to check out this guy's results. He's just using scare tactics. It's not that much. Then it would be less than. Or we could say, well, I don't think it's 35. Do you think it's higher or lower? I don't know. I just think it's not 35. And if it were not 35, then it would be this guy. So the relation, and that's what these things are actually called. They're called relations. The relation that you use in the alternative hypothesis either depends upon the phrasing of your counterclaim to the null hypothesis or what your sample suggests. You say 35% of the population goes to McDonald's. I talked to 100 students on class, 100 students on campus. 50 of them go to McDonald's. That's 50%. I think it's greater than 35%. As far as the other one, for example, the mean salary of men is equal to the mean salary of women. And this is a contentious topic. I'm sure you've heard of the pay gap, salary gap, the gender gap, if you will. There are arguments on both sides that it is a thing and it isn't a thing. So it's really hard to see who's doing the math right to compare apples to apples. I do not know the true answer to whether or not there's a salary gap based on gender. But in an ideal world, there shouldn't be, right? Yeah, I mean, your salary should depend on a lot of things, but your gender isn't one of them. What do most people contend about salaries for men versus salaries for women? Do y'all know? Different? Not just different. Most people are under the, most people who challenge that, challenge it with the fact that we think men make more than women. Now, there are areas where it's the other way around, where the average salary for women is greater than the average salary for men in certain areas, and vice versa in other areas. So really what the alternative hypothesis would be, at least in most people's minds, is no, we think it's this. And we have to fix that. And so the argument begins. Quick question. What if somebody contended that? Is it a problem? No, you see what I did, right? I changed it to average salary of men is less than average salary of women. Is that a problem? Guys, ladies? That's what do you think? I mean, I'm flipping the coin, if you will. Let's assume for a second that it's a fact that men make more money than women doing the same job for the same amount of time, okay? It's a problem that needs to be fixed. Can we agree on that? That, you know, there should not be an association between gender and salary. But what if, when all the numbers washed out, it was actually revealed to be the other way around? Is it still a problem? You'll see what I'm getting at, right? Yeah. Oh, I'm sorry, we did the math, and actually women are making more money than men. Never mind, go about your business. Wait a minute. I thought it didn't matter. Well, now we're not. All I'm saying is, and I'm not trying to say anything disparaging about men or women. I'm just saying something about people in general when they make an argument. People argue against things that typically, not always, but often go against them, whatever group they belong to. But when you flip the script, sometimes it's like, oh, it's not such a big deal. And if you look around, you'll see this all the time. And I'm not saying it's right, and I'm not saying it's wrong. I'm just saying it's a thing. That's all I'm saying. But that's not the usual contention. The usual contention is that. I didn't want to use greater than on both of them, but that's okay. The sign, the relation in the alternative hypothesis will vary from time to time, but it will always be one of these three. And I will tell you right now, in the process of hypothesis testing, it will be critical, it will be mandatory to nail this sign. The null hypothesis, not so much. That's why we just default to equal all the time. But it will be imperative that you get the sign correct, the relation correct in the alternative hypothesis. You'll see why in just a moment. Okay, so really that's the big thing from 4.1 that I wanted to carry over, is that there's two types of hypotheses. There's a null hypothesis whose abbreviation is H0. There's an alternative hypothesis whose abbreviation is HA. The null hypothesis is pretty much, this is what we think is true. The alternative hypothesis is a counterclaim, usually based on some sample evidence. And then the battle that ensues is our sample strong enough to reject your claim about your null hypothesis, your claim about the population, which takes us to the next section, section 4.2. And 4.2 is titled Measuring, I'll bump up the font size in just a second, and I'll spell measuring correctly, Measuring Evidence with P-values. I think I've asked this before, but how many of you have had a statistics class before, high school, college, or wherever? I know you have, because you asked me about Z's. Just one of you. Psych stats, maybe? Anybody gonna take psych stats, maybe? Okay, you're gonna see a lot of what we're doing in this class right now. You'll also see some of what's in stats too. So just letting you know. So some of you might know what a p-value is, but let me kind of whet your appetite for it by going back to the previous hypotheses. And let's pick on the gender one down here. Let's just focus on this. Oops, that's not what I wanted to do. Let's focus on, I wanted that in red. I'm going to make this do what I want. And I'm going to turn down my phone because it keeps going ding, ding, ding. Okay. All right, so let's say that people say that there's not a difference in genders and salaries based on gender, and somebody gathers some data that suggests otherwise. You know, you say there's not a difference, but I talked to 50 men who do this job. I talked to 50 women who do the same job. I calculated their average salary, and we got this. Now, let's say that in this sample, what we came up with, and remember it's a sample, so we would have to use sample mean, X bars. Let's say that somebody who was trying to refute the null hypothesis that the salary is the same regardless of gender, somebody took a sample and they said, well, we talked to men and we asked them how much they make per year. And of the men we talked to, their average salary was 60,000. And the women that we talked to, their average salary was 59,000. If the null hypothesis is true, let this sink in. If the null hypothesis is true about the population, and we take two samples that give us these means, do you think that this is strong enough evidence to say that the null hypothesis is wrong? Is it possible? Let me rephrase the question. Let's suppose that it is true that on average, men and women make the same amount of money. I talked to 50 men who do a job, their average salary is 60,000. I talked to 50 women who do the same job, their average salary is 59,000. Samples never perfectly agree with the population. That's just the nature of sampling. They are expected to deviate from populations by some. That's just the nature of sampling. Do you think the difference in these is strong enough to say, well, they're different, therefore the null hypothesis is wrong? Or do you think it's possible that even if the null hypothesis is true, there's a good chance we could find a sample of men whose average is 60,000, and we could find a sample of women whose average is 59,000. Do you think it's plausible for that sample to do that under the condition that the null hypothesis is true? You think? What's the average GPA on this campus? Throw a number out there. 3.2. Let's say we claim the average GPA on this campus is 3.2. Now, what's the average GPA of the people in this room? Let's say it's 3.25. Do you think if y'all's average GPA was 3.25, that would be strong enough evidence to say, well, the average for the whole campus can't be 3.2 because our average is 3.25? Or do you think it's possible, just possible, that this sample has a slightly higher average GPA than the whole campus? Yeah, it's possible. Of course it's possible. There may be some people in here with 4.0s. Not going to ask you to raise your hand, but if you're one of them, kudos. I can show you on 0 fingers how many semesters I had a 4.0. Because I got a B my first semester in English. Curse you, Dr. Morgan. No, he was a great teacher. I was just a lazy student. But no, when your sample disagrees with the population, that shouldn't surprise you. That's just the nature of sampling. Samples rarely perfectly agree with the population claim. The average GPA on this campus might be 3.2. Y'all's average GPA might be 3.25. That's not enough evidence to say, yeah, it can't possibly be 3.2 for the whole campus. Our GPA is different, but it's not different by that much. Now, let's say that somebody said the mean GPA for the whole campus is 3.2, but y'all's GPA was 1.5. Sorry, I didn't mean to make y'all dumber all of a sudden. Do you think that would be strong enough evidence to refute the claim about the campus? Probably, because if we took however many of you in here randomly from a population of students whose average GPA is 3.2, I would not expect y'all's average to be so far away from the campus average. So maybe the claim about the campus average would be wrong. Same thing here. Do these differ by a lot? Well, let me ask you this. If you make $50,000, oh, I'm sorry, I meant 60. Oh, I'm sorry, I meant 59. Or maybe I meant 60. Is your life going to be that different that year? With $1,000, you might think $1,000, yeah, but over 12 months, that's less than $100 a month. So it's not that big of a difference. And even though it does support the alternative hypothesis, it may not be strong enough evidence to reject the null based on the samples that were selected. Now, by contrast, let's pretend instead of this, it were, sorry, ladies, this is just to make a point. It were that. Now, would you say it's strong enough evidence to reject the null? I would. We're talking a massive difference now. Because think of it this way. If men and women at the same job truly made the same amount on average, meaning some make more than others, but that's just the nature of working a job, experience and blah, 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 blah. But if this were truly, if it were true that the average was equal, and then we grabbed 50 men at random and calculated their average salary, and then 50 women at random and calculated their average salary and got that big of a discrepancy, it is highly unlikely that this would happen if this were true. And by contrast, let's see if I can get rid of that. Well, I'll put the yellow back in just a second. By contrast, okay, that's the wrong color, but it's just the color it is. By contrast, it would not be that uncommon or unlikely for that to happen with the X bars if the null hypothesis were true. So there are some probabilities assigned with samples doing what they do if the null hypothesis is true. What's the probability that we would get the first X bar to be 60,000 and the second X bar to be 59,000 if the null hypothesis were true? I don't know. Maybe there's about a 25% chance that when we randomly selected these men and women, these are the results that we got. But if that happened, if men and women truly made the same amount and we picked 50 men and 50 women and got those results, that is highly unlikely to happen. The probability of that happening is probably less than 1%. So what's a p-value? A p-value is the probability of observing your sample if the null hypothesis was true. I'm going to type that out. A p-value is the probability of a sample occurring if the null hypothesis was true. A p-value is the probability of a sample occurring. I'm going to throw an asterisk because there's actually a little bit more to that. The probability of a sample occurring, comma, if the null hypothesis is true. And the gist of hypothesis testing is this. Let's start with the assumption that the null hypothesis is true. Then we observe this sample that was highly unlikely to happen if the null hypothesis was true. In fact, it's so unlikely that we question whether or not the null hypothesis were true in the first place. You ever try to catch somebody in a lie? Hey, if this and this and this and this, and eventually they say something that's not true, and then you backtrack and say, well, I guess the first thing was a lie. That's kind of what's going on here. If the null hypothesis was true, then we shouldn't have seen an example that was so unlikely to happen. But we did see an example that was so unlikely to happen. Conclusion, null hypothesis must not be true. So what's with the asterisk? Well, here's what's up with the asterisk. Give me 1 second to set up another text box and drop its font size down 1 notch. Really, what the p-value is not the probability of a sample occurring. It's the probability of a sample, oops, that's all caps, a sample we observed or one more extreme. Now, what do I mean by or one more extreme? Well, going back to the men and women, okay? I'll come back, a sample we observed, excuse me. A sample we observed or one more extreme. So what do I mean by that? Well, let's go back to the men and women for a second. And it's at 39,000. Without explaining where the numbers came from, let's just say for a moment that for this particular scenario, and I have no idea if this is the correct value, I would need more information. But let's say the p-value for this sample, that says value. Let's say the p-value is 1%. And what that would mean is if this null hypothesis were true that men and women truly do earn the same amount on average, then there's a 1% chance of seeing a discrepancy that big or worse. Right now, they're apart by 21,000. What's worse than being apart by 21,000, 22,000, or 23,000 or more? So when I say seeing the probability of seeing a sample that we observed or more extreme, I mean not just that, but that or worse. Now, again, I just made up the 1%. I have no idea if it's the correct p-value, but this is the measurement that we're going to use to pass judgment on the null hypothesis. So here's how this game is going to be played. Let me put the font size back where I want. Based on the null hypothesis being true, we calculate the p-value for the sample. Now, we haven't talked about how we're going to calculate that yet. If this p-value is, quote, too small, and we'll determine what we mean by too small in just a moment, but if this p-value is too small, then we reject the null hypothesis. And again, we haven't set up what is too small, and we haven't set up how we're going to calculate this p-value. But this is going to be our strategy. This is going to be our plan of attack. You claim something about the population in your null hypothesis. We have a sample that contradicts it and supports the alternative hypothesis in its place. Our sample has a certain probability of occurring under the assumption that the null hypothesis is true. Because remember, samples are going to deviate from the population, even if your claim is right. That's just the nature of sampling. But if what we observe in our sample was unlikely to occur because its probability, its p-value was too small, then what we're saying is we can't blame the discrepancy in our sample and the null hypothesis based on the fact that we just picked a sample at random. It's so far off, its p-value is so small, its probability was so unlikely that we have to assume that your original claim was incorrect. And again, this is just evidence. It's not 100% proof, but it's strong evidence to the contrary. So our plan for hypothesis testing is, you know what? I'm going to start writing this where we're going to fill in the gaps as we move forward. So without further ado, how to conduct a hypothesis test. I'm getting a little ahead of myself, but I'm painting the big picture. So I'm actually a little bit ahead of 4.2 right now. How to conduct a hypothesis test using what's called the p-value approach. And there are two approaches. There's another approach called the critical value approach. When we get to chapter 6, I'll introduce that, and then we'll have options for conducting hypothesis tests. All right, step number 1 is going to be state the null and alternative hypotheses. And these will always be symbolically. In stats 2, we get to a point where we can describe them in words and not symbols. But for our purposes, our hypothesis will always involve some population variable, some value, possibly, and then some claims about equality or inequality. I do want to remind you that these are always about populations. So when you write your hypotheses, HO and HA, you never mention X bar, you never mention P hat, you never mention R, you never mention any variable about a sample. It is always about a population. So it's okay to talk about a hypothesis involving mu, involving P, involving rho, or any other population value. There's another type that's not in this book about testing standard deviation. So it would be sigma, but it wouldn't be S, but we don't do that in this class or in stats 2. So your hypotheses are always about population. Step 2, from your sample statistic. And remember, all that means is whatever we measured from the sample. And it will always be the same type of variable that you're testing. So for example, if I'm testing about population mean, mu, then what I measure from my sample is X bar, sample mean. Or if I'm making a population claim about proportions, P, then what I get from my sample is a proportion, P hat. It's a battle of what do you say about the population versus what does my sample say? So from your sample statistic, calculate a p-value. And again, we'll get into the details on how to calculate a p-value here shortly, how to estimate one, and later how to flat out calculate it. And then your third step is pretty easy. If your p-value is too small, and again, I haven't defined what I meant by too small. I'm about to do that, which is why I put an asterisk on that. But if your p-value is too small, then we reject the null hypothesis. Meaning our evidence is so strong because our sample was so unlikely to happen under the assumption the null hypothesis was true. Then we say, well, we shouldn't have seen that. So our null hypothesis must not have been true. We reject it. Otherwise, we failed to reject the null hypothesis. I remember last time I saw y'all on Monday, we talked about when you make a decision, you only say one of two things: reject the null hypothesis or do not reject the null hypothesis. And it's worth pointing out now that it is the null hypothesis that is on trial. It is the null hypothesis that we pass judgment on. It is not the alternative. The alternative stirs the pot. Oh, you say this, I say otherwise. Here you go, sample evidence. Go get them. Rah, 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 rah. And at the end, one of two things happen. The null hypothesis goes, I'm still standing because you failed to reject me. Or the null hypothesis caves under the evidence and says, oh no, I got rejected. Your evidence was too strong because you saw something that was highly unlikely to happen if I were true. All right, so what do I mean by too small? Normally, too small is less than 5%. However, sometimes other, I don't want to say boundaries, we'll say significance levels. I'm kind of getting ahead of myself. I haven't defined what a significance level is, but it's basically the boundary that will accept seeing something. And if we cross it with our p-value, then we go, oop, nope, 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 not that. Sometimes other significance levels will be provided. And again, that will make more sense when we actually start doing hypothesis tests. And small typically has an M in it. Too small is less than 5%. However, sometimes other significance levels will be provided. So if you're doing a hypothesis test and they don't give you some percent to compare the p-value to, you just assume it's 5%. I don't know who made the decision on 5%, but that seems to be industry standard. And in stats too, very often we're not given a level to compare the p-value to, so we just assume it's 5%. All right. So that's all there is to hypothesis testing, but there's clearly some things we need to clarify. Really, the one thing we need to clarify at this point is the second step about calculating a p-value. Remember, all a p-value is the probability of witnessing something that we saw or more extreme under the condition that the null hypothesis was true. So how can we calculate a p-value? Well, really, at this stage, we're not calculating a p-value. What we're going to do is estimate a p-value. There is a formula, so to speak, for calculating a p-value. We'll get to that once we get through chapter 5. And when we get to chapter 6, we'll start calculating p-values instead of estimating p-values. Does anybody have any questions about the steps that I have written up there or why I highlighted the second one? Then I have a question for you. Why did I highlight the second one? I highlighted the second one because it's the step we need to figure out. It's the missing piece of the puzzle, isn't it? I may be wrong. Are we okay with this part? It's what we did on Monday. Are we okay with that part? That part's easy. Once you get this p-value from step 2, just look at it and see if it's too small, aka less than 5%, unless a different boundary is a different significance level is given. So the first part, most of the time, is pretty easy. It takes some thought. The last step is crazy easy. You just look at the number and go, that's less than 5%. We reject the null hypothesis. The trick is remembering when to reject and when to not reject. And the trick to remembering that is to remember that the p-value is the probability we saw what we saw. And if the probability that we saw what we saw was too small, well, imagine this. We'll pick on guys. Guys, you're at a place where you pick up girls or other guys. I don't judge. And you walk up to somebody, you know, you look, I like the way you look. You seem friendly. Would you go out on a date? And they say, well, there's a 25% chance that I'll go out with you. Do you like your chances? Yeah, it's 1 in 4. Maybe they'll flip a coin twice and do something. But if they said, there's a 1% chance that I'll go out with you. Are you liking your chances? Probably not. The p-value is like the probability of being that date offer being accepted. And if it's too small, then you pretty much get rejected. I know, but you say there's a chance. What's that from? Dumb and Dumber? I don't know. I've never seen it. Somebody told me. Is that where it comes from? Okay, I never seen the movie. I just know lines. But yeah, if your p-value is too small, you saw something that was highly unlikely to happen if the null hypothesis was true. It was so unlikely that we shouldn't have seen it. Oh, I guess the null hypothesis wasn't true. So p-value too small, reject the original null hypothesis. So all we got to do is figure out where to get this p-value from. So that's what the rest of this section is about, calculating p-values. Excuse me, estimating p-values. So how do we estimate p-values? Well, remember the bootstrapping? Just a reminder how that goes. We have a sample, we'll say of, well, let's say it's you guys. And we want to know the mean GPA of all the campus. We could calculate y'all's average GPA, or we could do the following. I'm not about to ask you your GPAs. I could write down all your GPAs. Let's just say that there's 25 of you in here. I think it might be a little bit more. Let's say I write down 25 GPAs, and then I wanted to do a bootstrap sample distribution. I would have to pick 25 numbers from your GPAs. But remember, when you do a bootstrap sample, you can pick a number more than once. It's like picking numbers out of a bag. All right, let me pull one GPA out of here. 3.0, let's put it back in, shake them up, pick another one. 2.5, put it back in, shake it up, another one. 3.0, wait, is that the same 3.0? Let me see what name it is. It's this, I picked the same person twice, but that's okay, because when we have a random and representative sample, we're assuming that each person in the sample represents multiple people in the population. So picking you twice just means I picked you and I picked somebody like you. So when we do this bootstrapping sampling, where we pick, what I say, 25 GPAs, where I pick 25 GPAs out of the bag, but I may pick some of them more than once, and then we calculate that sample's average, and we do it over and over and over and over again and get all these dots on a dot plot, that's bootstrapping. So are we going to do bootstrapping? No. We're going to do something like it. We conduct this is a fancy phrase, randomization distribution. This is where we simulate picking samples. And when I say picking samples of the same size as the observed sample, because remember, working on the premise that we already have a sample that we observed. Average GPA for the whole campus. Let's look at the average GPA for the sample of students in this room. But a randomization distribution is where you simulate picking samples of the same size as the observed sample under the assumption the null hypothesis is true. And you may be wondering, how do we do this simulation? How do we simulate picking another 25 people, but not bootstrapping? Meaning I don't take y'all's GPAs, throw them in a bag, pick and write 25 GPAs, but I can pick some of them more than once. To do this requires some math that we haven't gotten to yet, but technology that we have access to. So I'll show you what I mean. But let's finish this. We conduct a randomization distribution. This is where we simulate picking samples of the same size as the observed sample under the assumption the null hypothesis is true. Then we form a dot plot for the same sample statistic as we observed. In other words, I simulate picking 25 students under the premise that the average GPA is whatever we claim. And I'll admit that we would also have to know the standard deviation, but let's not worry about that right now. And then we make a dot plot. Then we see what proportion of those samples, dots, if you will, because we're going to be looking at we're not French. Then we see what proportion of those samples dots are what's the word I'm looking for? Are the same or more extreme than our observed sample. This will make more sense when you see the picture. But basically what we're going to do is we're going to make a dot plot or have one presented to us and see what proportion, what fraction, what percent of those dots match our sample or are more extreme. And we're going to do one with you guys. It's not about GPAs, don't worry. We're going to do just proportion. But in order to do this, I need to think of something that I can say X% of the campus does something. And then I'm going to survey you guys to see what percent of you guys do something. So first we got to come up with something. So what do I want to speculate about all students at UT Tyler? A certain percent of them, what? Say it again. Participate in extracurricular activities. I like that one. It's non-controversial. I'm not going to get in trouble. Thank you. I hope. All right. So for example, Now, I don't know if anywhere on the UT Tyler website it says what percent of students participate in extracurricular activities. If anybody wants to try to search that real quick, I'd appreciate it. I'm just going to guess a number. I'm going to guess 27%. I totally made up that number. UT Tyler claims 27% of its students participate in extracurricular, I think that's one word, activities. Well, I know it's not spelled that way. There we go. I will put a hyphen in there. In a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Got some mighty fine estimating skills, I do. In a sample of 25 students. Now, before I ask you to raise your hand if you participate in an extracurricular activity, let's make sure we well define what that means. Sports, any club, any sorority or fraternity. Is there anything I'm leaving out? Sports, club, sorority, fraternity. Can we just assume that you know whether or not you participate in one of those? Yes. Music. Okay. Some type of band, orchestra, choir, whatever. Okay. So we'll throw that in there too. So let's just say anything that you do besides just going to class. I think that's reasonable enough. All right. Quick show of hands. Keep them up so I can count them. How many of you participate in extracurricular activities? Keep them up, please. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Thank you. In a sample of 25 students, 15 participate in extracurricular activities. Okay, now whether or not you did or didn't or raise your hand correctly or not is actually quite irrelevant. I just needed to formulate some numbers here. So thank you for participation. Does this provide evidence? And I'm going to say at 5% significance. And again, I haven't really told you what a significance level is, but when you're given this boundary that you compare your p-value to, it's called the significance level. Does this provide evidence at 5% significance that UTT's claim is incorrect? Okay, so we're going to do our first hypothesis test, our first legit hypothesis test, made up with you guys and a made up claim about the university. All right, so if we're going to do this hypothesis test, the first thing we should do is state our hypotheses. That is always step one in a hypothesis test. So number one, state the hypotheses. Okay, so let's state them. The notation is H0 for the null and HA for the alternative. And I do want to remind you that these symbols are not variables. You do not say they equal anything. They are abbreviations for the phrase null hypothesis and alternative hypothesis and should be followed with a colon. Now, can anybody tell me UT Tyler's claim, made up claim, symbolically in letters and numbers? It can't, don't write this down because it's wrong. First off, it can't be that. Because if I'm going to be testing mu, what is mu the variable for? Population mean or average, if you will. In anywhere in the problem, do you see the word mean or average? You do not. Okay. And anywhere in the problem, do you see the word proportion? You don't. Do you see the word proportion? I don't. I didn't type it. However, the number that they gave us was a percent of a population with a characteristic, which is the definition of a proportion. So if you're given a percent, you're probably given a proportion. If you're given a percent, you're probably given a proportion. So it's a proportion of a population, it's P. Now, you could write 27% or you could write 0.27. Both are okay. But in the long run, you don't do math with percents. You do math with decimals. Percents describe things. They're horrible for doing math with. But when you're just writing the hypotheses, either one would work. Now, that's our null hypothesis. But what should the alternative be? You know, it might help if we knew what % of you participate in extracurricular activities. So when I gathered the data from you guys when you raised your hands, I should have went ahead and turned it in. Well, maybe I didn't know at the time, but now that I know that I'm testing a population proportion, the evidence I gather comes from a sample, and the variable for a sample is p hat. 15 out of 25 of you have this characteristic. I think that's 60%. How would you see if that's 60%? How would you turn that into a percent? Yeah. How would you figure out what percent that is? Divide it to get a decimal. And I think when you divide it, you get 0.6. I'm waiting for somebody to 0.6. Now that number in itself is in a percent, but does anybody know what percent that is? Do we need to have the discussion about how to turn decimals to percents? Okay, some of you say no, but I think some of you I might need to, so I'm gonna say it once. To turn a decimal to percent, move the decimal 2 places to the right. So if I move the decimal 2 places to the right, I would have to throw in an extra 0. So 60% of you go, well, I don't know what just happened there. I don't know what happened. What is going on here? 60% of you have this characteristic, or as a decimal 0.6. So knowing what we know about your proportion, this class's sample proportion, what do you think we should say about the university's claim? And let me give you a little bit more guidance. Our alternative has to be about proportion. It has to be about 27%. So the real question is, what am I going to put between them? I could put not equal. There's one other thing I could put. Greater than, because our evidence could be looked at as one of two things. Number one, 27% is wrong. It's something different. Or even stronger than that, we think it's more than 27%. Now, the interpretation from words to symbols in the alternative is critical. So I want to focus a little bit more about the question that was being asked. Does this provide evidence at 5% significance that the claim is incorrect? So if the claim is incorrect, what must we put in the alternative? You say it's 27%. I say it's wrong, because you say it's equal to, but I say it's not equal to. Now, it would not technically be wrong without a clearly stated question to put greater than in there. In fact, I know some of you are super meticulous at writing things down, but for reasons which aren't clear yet, I need to change the wording of the question. Okay, because otherwise I'm setting you up for something I haven't prepared you for yet. And I should have seen that before I wrote the question. So this is what happens when you do freestyle math off the top of your head, no prep. Well, it's not totally unprep, but I'm going to change the statement of the question. And again, my apologies, especially if you've written this down. Does this provide evidence that, and I'm just going to change the last part, it's greater than 27%. And again, I apologize for changing the question, but trust me, there's a reason why I didn't want it to say not equal right now. And for those of you done hypothesis testing before, I didn't want to do a two-tail test yet. And if you don't know what that means, don't worry, when the time is right, you will. But with that question, I think it's pretty clear what the alternative is suggesting. Based on your numbers, we think it's greater than 27%. And I really did want a greater than sign in the alternative hypothesis. Okay, so assuming that I put the question up there like that at the beginning, does anybody have any questions about why the null or alternative hypotheses are what they are? Okay, next, we need to find the p-value. Now we're going to find the p-value, and in this case, we're going to do it using a randomization distribution. And I haven't illustrated what that is yet. I'm about to right now. In order to find the p-value, we first need to create this randomization distribution. It is built on the assumption that the null hypothesis is correct, that the p is equal to 27%. So I am going to switch over to the internet for a second, which is right here. And I'm going to go into StatKey, which is right here. And this is going to present the same dilemma as before, that if you went into StatKey and did what I'm about to do, you'll get a slightly different but fairly similar result to what I'm about to show you. We're in this last column titled Randomization Hypothesis Test. I think it should be obvious, but does anybody know which of these 5 I'm about to click on? Test for a single proportion. So because we're testing one proportion, we may test different proportions. I wonder if the percent of men is the same as the percent of women, but we're not doing that right now. We're going to click test for single proportion. Now, what this is going to do is it's going to simulate sampling however many people from the assumption that the null hypothesis is true. So what I have to do is I have to tell it what my null hypothesis is saying. The null hypothesis that I completely made up was 27%. Okay, now what I'm going to do is tell it to generate some samples. Can I change the sample size? I'm not sure where this is left over from, but let me try something real quick. Okay, I'll be honest. I don't know why it is defaulting to a sample size of 25. I wanted it to be 25 because there were 25 of you, but that's good. So now I'm going to tell it to do this. All right, computer, I want you to simulate picking 25 people and figuring out what percent of them have this characteristic using some math that we're not getting behind the scenes of. This is where the author fails me. They don't get into where these numbers come from. But I'm going to click generate 1,000 examples. 1,000 samples. So what StatKey did is said, all right, let's assume that 27% of a population has a characteristic and we randomly pick 25 of these people. What's the p-hat value for that sample? For example, right here, there's a dot that says, well, we counted 8 out of 25, so 32% of them had a characteristic. We got an extreme one over here that said, and look in the bottom one where it says randomization sample on the right. All right, we did a randomization, and in this random sample, 14 out of 25 of you had a characteristic for a p-hat value of 56%, where it says proportion on the right box in the middle of the screen. All right, so we've got this randomization distribution. We simulated picking samples of size 25 under the presumption that the null hypothesis was true. And each of these dots, they're so stacked, they look like they're lines, but each of these dots generated a p-hat value. Now we can find the p-value. You got to be careful because I just said p-hat and I said p-value. Those are two different things. P-hat is the proportion of a sample with a characteristic. P-value is the probability that we would have seen what we saw in this class. Now, what percent of you? What was it, 60? Okay. Let's look at the scaling here. 0. I don't like how these are set up. This goes with that. I know it's not clear. I wish it was right under it, but it was. So this little line is the samples where 10% of them had a characteristic. This line is the sample where 20% of them had a, hold on. Do me a favor. Hold on, Zoom folks. It's the percent of this random sample that had a characteristic. This one was not. Do me a favor, watch that. Watch the number. And for those on Zoom, watch this number right here. All right. So our p-hat values go from 0 to 4% to 8% to 12%. 16%, 20%, 24, there's a pattern emerging, 28, 32, 36, 40, 44, 48, 52, 56, and then it stops there. So the most extreme one, and this was a bad example because none of them up there are 60% or more. You guys were 60%. I'm not going to change the problem, but just for kicks and giggles, Let's pretend that this last stack over here was 60%. I know it's not, it's 56%. You guys were too extreme compared to my fake claim about 27%. Oh, wait a second, I could go back and change the 27 real quick. I'm not going to do that. All right, so here's what we would look for, and unfortunately, this isn't the best example. The p-value is the percent of these dots whose proportion was yours or higher. Y'all was 60%, right? 60% of you participate in an extracurricular activity. What proportion of these dots are 60% or higher? Well, there's none of them because the biggest one that we had was 56%. But just for fun, let's pretend that this says 60% at the end. It's not, it's 56%. I can't tell how many dots are in there, but maybe if I do this, watch closely. Wait, come back. Watch closely. I will not be defeated. I take that back. I think there's 2 dots in that stack. All right. And I say that because as I move the pointer up, you can kind of see that there's just 2 dots there. So let's pretend for a second that there's 2 dots on this dot plot that are as extreme as you guys out of 1,000. All right, let's go back to here. All right, jump into this text box. All right, from the dot plot, out of 1,000 dots, only 2 had a p-value, had a proportion, p-hat, that was the same as or more extreme, because we were talking about being greater than, our observed p-hat of 0.60. And again, that's not actually even true. On this particular one, the most extreme one we saw on the right end was only 56%. So actually, there were none, but I didn't want there to be none. But from the dot plot, out of 1,000 dots, only 2 had a p-hat that was the same or more extreme as our observed p-hat of 60%. So the p-value for our observed sample is 2 out of 1,000, which is 0.002 based on this randomization distribution. I'm going to do it again in just a second, but I didn't want to change the problem, and I'm just going to talk it because I know we're almost out of time. So if the claim about UT Tyler and students participating in extracurricular activities was true, there's almost no chance that you guys would have raised your hands like you did. Because if we turn this to a percent, it's 0.2%. That is very unlikely to happen. So if the claim was true about UT Tyler, 27%, there was less than a 1% of chance that 60% of you were going to raise your hand. That is so unlikely that our claim must not have been true. Third step. Since this p-value is less than 5%, we reject the null. So you guys provide strong enough evidence that my made-up claim was completely wrong. Okay, now I want to contrast it to something. I'm not going to write this down, but I just want you to witness it. Maybe I should have said something like 50%. Half of UT Tyler students participate in extracurricular activities. Okay, 60% of you. Do you think your 60% is strong enough to reject the claim that half of students do? Let's find out. I'm not going to write this down, but I want you to watch. So I'll give you a second to finish writing this. I know some people are writing. If you are writing, do me a favor. When you are done, with authority, put your writing utensil down so I can hear that you put it down. And if I see anybody writing, I'll pause for a second. But while they're finishing, this is what I'm going to do. I'm going to go back into stat key. I'm going to change the 27% to 50%, and then I'm going to tell it to do the thing again, not with as many dots. We're going to count how many of them are 60% or higher. Looks like everybody's done writing. And if not, I'm sorry, but I'm going to go back to stat key for a second. Give me 60 seconds, folks. Watch this. I'm sorry, it wasn't 27%, it was 50%. That's what they said. Did anybody actually find a stat on the UT Tyler website? That's all right. And let's say I generate 100 samples, so it's easier to count the dots. Now, your guys' p-hat was 60%, right? How many of these dots are 60% or higher? Well, look on the bottom box over there. You see it says 60%. So 60, 64, 60. So all these starting here are higher. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22 of these randomized samples were as extreme as y'all or more, meaning 60% or higher. 22 out of 100, what percent is that? 22%, because percent means per 100. So you guys would not be strong enough, because if the claim was right about half of students participating in extracurricular activities, according to this, there was a 22% chance that I was going to see 60% of you who said, yeah, me. Well, 22 isn't that unlikely. It can happen. So we would fail to reject because our evidence wasn't strong enough. It wasn't that unlikely to see that happen under that null hypothesis. We're going to continue this discussion next time. I'm not going to give you a homework assignment over this for now, because I want to have a more I want to conclude the discussion later. Okay. So one homework assignment, keep an eye on the quiz for 4.1. Thanks for your time, folks. Zoom folks, if you have any questions, drop them in the chat. Otherwise, you're free to go. Thanks for participating. By earlier, do you mean earlier that day or earlier in the week? Both. Whatever works for you. Yeah, we can do it earlier in the day. What I can do is I can leave an exam with the secretary. Dealing with the secretary's office.
For the math?
Yeah, it's on this floor. Do you take the elevator or stairs?
I walk.
Okay, so when you come up the stairs and you come onto the 4th floor, you go to the right to go to this way, but if you look to the left, you'll see that glass door, the glass wall. That's where the secretary's office is.
Okay.
What I'll do is I'll give her the test. At some point, let me know what time you want to take the test, so she'll know when to expect you. And what she'll do is she'll set you in a setting where you can take the test, and then you'll just give it back to her.
Do you want me to remind you as well, like in the upcoming week?
Yeah, probably the Monday before the test. So
Okay.
the first, remind me so that I can send the test to her. Okay.
Okay, thank you.
Hey.
So I have a question. I've been pretty much everything where just like the big problem was like.
I was afraid of like Louis shake the
I was wondering if we could meet before the next class to see like if I'm right, like I did
Yes.
last time. Like on Monday.
We can. Yeah, I was trying to remember. Was I going to meet with you today, but I didn't see a text saying where are you, so I thought it was okay.
I was wondering exactly what it was asking. I was
Okay,
thinking,
the answer to this is no. Because what you're going to do on this one, let me kind of describe what
Oh,
you're going to do.
man.
All right, we have 100 dots. We're trying to catch 95% in the middle, which means the other 10% on the ends, which means 5% on the left, 5% on the right.
You're like,
Okay.
you brought
Now,
the.
so it's 5. So, so what you're going to do is you're going to count to find the 5th dot starting on the left. 1, 2, 3, 4, 5. So whatever number that is, and it's actually this number. When I gave an example, I was like, it's going to be that. So the 5th dot from the left is at this number. Where's the 5th dot from the right? 1, 2, 3. It's somewhere in this stack. So yeah, it's somewhere in that stack. So your left end is where the 5th dot is over here, which is halfway between these two numbers, which is actually this number. But do you understand what I mean when I say the 5th dot from the left?
yeah.
Okay.
Counting it.
Right, so you're counting in the correct number of dots, and then you're seeing where those dots are. And those two numbers are what the answer to this is going to be. So we're not going to do this. We're counting dots from the outside. And you do the same thing on the next one, but when you get to it, you'll find out it's also 5 dots.
If you could tell the schools.
Yes. Mhm. So that's 5% there. 6 is 5%. Number 7 is 5 dots. They both happen to be the same number. Right. Yeah. Right. Because what I was trying to do is go, okay, so there's 90% in the middle, so there's 10% in the outside the middle. So that's 10%. You know why it's 10, right?
the two sides.
Right, because 100 minus 90 is 10.
Hold up.
Probably. I've never actually seen that.
90%
I've seen sorority culture, those was,
these
I spent one
are
semester
the
at
remaining
Wolf.
2%.
1 year at
And
SFA.
the next step says cut that in half, so lose 5%.
What were you saying? Sorry.
So the purpose of this question was to understand what the 90% means. The middle 90%, leaving 10% to get cut in half with the two ends. And then because it's 100 dots, 5% equals 5 dots. And 5% equals 5 dots because it was 100 dots total. But in the second one, it's more dots and it's a different percent. But I'm telling you right now that it ends up being 5 dots also. Okay, and then you just count off the dots from the ends and you see where they are, and those are the two numbers for your
I did not
interval.
like it.
Okay, so, pretty much like just do what I did here on this other problem.
Yes, it's the exact, it's just a different setting, but it's the same flow. The only difference is it's a bigger percent, but it's also a bigger samples. But at the end, it ends up being 5 dots. You end up taking 1% of 500 versus 5 dots.
Okay, alright, thank you.
You're welcome.
Never that good old time.